Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a clever paper from June 9, 2025, titled, Well Begun is Half Done, Low Resource Preference Alignment by Weak-to-Strong Decoding. It tackles the challenge of aligning LLMs to avoid bad outputs, which can sometimes hurt performance on other tasks, a problem known as the alignment tax. The authors found that the hardest part is getting the beginning of a response right, so they propose weak-to-strong decoding. A small, aligned model drafts a good beginning, then a large base model takes over to finish. This approach improves alignment without the usual performance cost. Now, the core idea behind this weak-to-strong decoding is that a smaller, aligned model, which they call the draft model, generates the initial part of a response. Then, a more powerful but less aligned base model continues from that safe starting point. And if you want to experiment with this yourself, the authors have released all the code. Their GitHub repository includes an execution script, instructions for using your own data, and even their pre-trained Pilot 3B draft model to get you started. And the paper kicks off with a great little illustration to visualize this whole idea. In the first panel, you see a big robot, which stands for the powerful base LLM, stumbling on its own. It's struggling to align with what we want. Then, in the second panel, a smaller, friendly robot, representing the small, aligned draft model, comes in and gives the big one a hand. And finally, with that well-aligned start, they succeed together, finding a treasure chest. This image perfectly captures how a good beginning helps guide the entire process to a successful, aligned outcome. And the data from their preliminary experiments really backs up this intuition. The top chart shows that for models like Llama 370B, their perplexity rank is mediocre. Perplexity is a measure of how surprised a model is by a correct answer. So a mediocre rank means the model wouldn't have naturally generated it. But their reward rank, which scores alignment, is almost perfect. So the models know a good answer when they see one, they just struggle to start it. The bottom chart confirms this, showing a huge spike in perplexity at the very beginning, which then drops off. This tells us getting the start right is the hardest part. So, building on that idea, this next figure shows us exactly how this weak-to-strong decoding framework works in practice. After a user asks a question, you can see the small draft model starts generating the response, token by token. Meanwhile, the large base model is checking each of these tokens, and its confidence, shown by those green bars getting taller, keeps increasing. This is all part of their auto-switch mechanism. It's looking for the point where it's sure the response is heading in a good, aligned direction, which is determined by a confidence threshold they call gamma. Once that threshold is crossed, the base model takes over to finish the job. And this figure really highlights the problem that this whole method is designed to solve, the alignment tax. Here the researchers show what happened when they fine-tuned a small llama model to create their aligned Pilot 3B draft model. On the left, you see the Alpaca Eval2 score, which measures preference alignment, more than doubled. That's a huge win. But if you look at the other two benchmarks, GSM 8K for math and Human Eval for coding, the performance actually dropped. This trade-off is the alignment tax, and it's what weak-to-strong decoding aims to avoid. So the key question is, does this weak-to-strong decoding method actually avoid that tax when applied to a large model? And this table gives us a clear answer. It looks at those same math and coding benchmarks, GSM 8K and Human Eval, for several large models, and what we see is pretty remarkable. Instead of a performance drop, the scores consistently improve. For instance, with the Gemma 227B model, the Human Eval score jumps from around 63% to nearly 66%. This result is a huge deal, showing weak-to-strong decoding successfully aligns the model without that costly tax. Alright, so we've seen that weak-to-strong decoding avoids the performance drop on other tasks. But the real question is, how well does it actually do the alignment? This table gives us the answer. It compares weak-to-strong decoding against a whole suite of other methods on benchmarks that measure things like helpfulness, harmlessness, and truthfulness. And the results are just dominant. Across all three models shown here, Llama 3, Llama 3.1, and Gemma 2. Weak-to-strong decoding, highlighted in green, consistently scores the highest. Just look at the HHR-LHF total score for Llama 3.1. It jumps from about 58 for the base model all the way up to 97. That's a massive improvement in alignment. So this raises a really interesting question. Why does this method work so well without that alignment tax? Well, this chart gives us a big clue. It shows us when the auto-switch mechanism decides to hand control from the small draft model to the large base model. For the GSM 8K math problems, that blue line shoots up really fast, meaning the switch happens very early. But for the Alpaca Eval 2 alignment task, the orange line shows the switch happens much later. This suggests that for math, just a small nudge is needed, while for alignment, the draft model has to set the tone more thoroughly at the beginning. This idea that the initial guidance is what really matters for alignment is a powerful one. The weak-to-strong decoding method shows we can achieve excellent alignment without that dreaded performance tax, essentially getting the best of both worlds. This research is a huge step forward, making it much more efficient to align powerful models. That's all for this week's AI Research Roundup. Thanks for tuning in, and I'll see you next time. I'm Alex.